Thank you for attending the seminar. I thank you, the participants, for that. I'm going to talk about site investigation. I'm not going to cover everything because in 2 hours is too much. It's not. It's not. It's not enough. Just the opposite. My name is Alberto Ortigo. I was for a long time a professor at the University of Rio de Janeiro, professor of geotechnical engineering, and I entered the market long ago. And the company that I work for is TerraTech International, which is a US-based company. I'm also a fellow of the uh, Institution of Engineers and a PE in a few states. Let's go ahead. The main reference for uh, this webinar are two of my books. They are not particularly devoted to site investigation, but they cover some stuff, so you can use as a reference. Also, I'm going to refer to these guides to confrontation tests by Peter Robinson, something that you can download from the web. It's available. And also my friend Fernando Schneider's book, In-Situ Testing in Geomechanics, which covers a lot of things. The main in-situ tests that we are going to cover are the SPT, the CPT. We are going to talk a little bit about the VST as well, but we don't have time to talk about the DMT, the dilatometer, and the pressure meter. This would be another seminar, hopefully. Well, let's start by talking about boreholes and sampling, which is the oldest way of doing site investigation by digging a borehole and obtaining samples for additional testing. And here we have a series of uh, uh, different types of samplers that can be used. If you have a soft clay like this, probably the best way to do the best way to collect a good sample would be with a piston sampler, stationary piston sampler, which we're going to address. Shelby, if the soil is a little bit harder, Shelby tubes could be, or thin walled samplers could be used. For hard soils, we use the Denison sampler, which we're going to address. And if we have, silty sand, etc., split barrel sampler is could be used. And once we get into very hard soils, we have to use rotary drilling and with special samplers for rock sampling. Okay, and since I started working very long ago, uh, there was a tremendous development in terms of quality, in situ testing different, and also very much in health and safety, workers' health and safety in the field, which I'm going to address briefly. So we have here what type of drilling rig from 1960, no equipment to protect the workers. And recently you have much tougher rules to do that, but also there some of them are too tough. I think they are not normal in my view. And this kind of protection, there some mainly mining companies require. They are crazy about safety and everything related to the workers' health and safety. So they require this kind of screen or protection. And this is a large hydraulic rig which we operated in the past and very effective. In general, you can, with a drilling rig like that, we can do 20, 30 meters of boreholes per day. Also, this is something when I started we didn't have, which site safety organization with these tents for people to have their meals and protections, etc., etc. So this tends to be normal now in mainly with the mining companies. Uh, I'd like to address first the SPT. SPT is very old. In the past, this is uh, something that took place in the 60s. We just use a tripod, and the SPT is the standard penetration test is standardized in many standards. Certainly in America and Europe, etc., etc., is used all over the world. And in the past, we used a hoist like this. It was hand operated by the operator here. This is what was very common in the past. Now and uh, what's the SPT? The SPT sampler is a sampler like this. It has outside diameter of about 50 millimeters. The inside diameter is 35 millimeters, and then it is a thick walled sampler. And what about that? Thick walled sampler disturbs or removes the sample. So what we get with this kind of test is the number of blows to drive the sampler, which is the N value, which I'm going to address, and we get remoted samples. So no undisturbed samples with this equipment. The other evolution that took place, we went to manual SPT, and in most cases, now we can use the automatic SPT. So it's not anymore hand operated, but there is an engine that gives the blows, and in some rigs, the number of blows is automatically recorded. So the SPT, we use a standard sampler, 50 millimeters outside diameter, 35 inside, so thick wall. The height of fall is 75 centimeters, and we apply a drop hammer, which is standardized at 63.5 kilograms. Okay, that's the mass of the drop hammer, and the casing, or usually 63 millimeter diameter inside diameter, and we count the number of blows to penetrate 30 centimeters. As a matter of fact, we drive in 3 sections of 15 centimeters, and we use the last 2. So the N is the blow count to drive the sampler 300 millimeters, and N is the SPT index, okay? And then we have to calibrate the, or reduce or change the SPT index from uncalibrated values to to a standard energy of 60%. And I'll show you this later on, okay? And this is the kind of borehole log that we come up with. This has been recently done for a very large bridge project in Guyana, in Georgetown. That's the Demerara Bridge. And as you see here, the first 6 meters, the SPT is 0, which means that the soil is very soft, and then it starts to increase. You know, here you have SPT of 10, okay, and 10 is a reasonable number, and this goes. Now we are at the depth of where's the depth? Oh, somewhere here. Sorry. The depth is here. So we are at the depth of nearly 40 meters, and this borehole goes down to here's 50 meters. Okay, and then when it reaches refusal, we have to use rotary drilling to go beyond that. And these are the samples that we get. Now it's a different type of sampler, not SPT anymore, because you're using rotary drilling. One requirement that's new standards like those European STM, LBNT, these some standards now require that the energy of the SPT should be calibrated. I mean, every rig should be calibrated once a year. And in order to do that, we use this kind of SPT analyzer. It's very much the same as when we do dynamic testing on piles, more or less the same. The equipment is similar, okay? So we use transducers to measure. They are attached to this piece of rod, and then we apply the blows, and we measure the amount of energy. And in most cases, it's from 30 to 8%. It varies a lot depending on the mechanical aspect, mechanical design of the equipment, etc., etc. And then we would be able to calibrate and adjust the energy for the N60, which is in most cases the standard, the 60% energy applied to the sampler. Let's have a look at the interpretation of N value. N is the SPT index, okay? So if N is less than 4, we can say that we have soft clay or very, very loose sand. Usually sand gives higher values. Most sands that I have had tested in the past, they yield values from 4 to 10. So loose to medium sand or stiff clay. A clay with SPT of 10 is very hard, it's very stiff, okay? Then very stiff clay or dense sand from 11 to 30, and over 30, very stiff material. Usually, what we are concerned for a foundation, as a foundation design, for you to have an idea, if we have a SPT of 10, in most cases, we can use a shallow foundation, while less than that, in most cases, we have to drive piles, okay? So this is more or less when we have a SPT of 10, the soil is going to deform not very much, in most cases, not all. If you're looking at a bridge or something like that, in which we have very high loads on the piles, these piles should be usually bored into the rock bottom with the socket, okay? Well, let's have a look at the undisturbed soil sampling. The best way of doing soil sampling is this: undisturbed block sampling, with this methodology which explaining in many manuals, standards, and books. But this doesn't apply to very soft material, and we can only obtain these block sampling at a shallow depth. Well, I have used this kind of sampling for if I'm analyzing a dam and I want to have strength parameter for a dam, deformation parameters, I would recommend use this. But in most cases, you cannot go very deep. You go 2-3 meters below the surface, and that's all. And sample quality. If this is a classification that a friend of mine, Saketo, came up with, and I'm using that from him. So we have these are geotechnical characteristics that you may be interested on, and which type of sample quality that you're looking for. So if you are looking at only nature of soil, particle size, water content, you just rely on removed samples from the SPT or something else. But you really want undisturbed sample. Then for mainly for mechanical behavior, I mean stress parameter, Young's modulus, etc. We need much higher quality, and I'm going to address this. Uh, the for soft soil, the best way of obtaining some good samples is with a Shelby or a large diameter Shelby, or better yet, is the stationary piston sampler. So this is a thin-walled sampler. Usually, this length of the sampler is 6 centimeters to 8 centimeters. It has a valve here. When you push into the soil, water gets in, okay? And this valve opens and leaves the water to go out. And when you finish the pushing the sampler, this valve, this ball valve closes, and then you push, you recover the not push, you recover the sample with the valve. This valve is closed, okay? This is the standard procedure to get samples. But this is much better. If you have a large diameter stationary piston sampler, what you do is the piston remains in place, okay? That's the advantage. You push the sampler, but the piston remains in place. And what happens? When you pull it out, the piston provides vacuum on the top of the sample, so the sample remains in the sampler. Okay. Uh, Many years ago, I did a I did a research on this. This was part of my MSc thesis long ago. I spent a lot of time in the laboratory uh, doing tests, and I decided to look at which sample was the best. And I did with this was the standard practice at the time, 50 millimeter diameter, 63. I don't remember. This should be 75, and the larger one, this one, was 125 millimeters. So much larger uh, sampler. And this is kind of clay that I did this research. It was a clay deposit very, very close to Rio de Janeiro. So the IP is about IP. I mean the difference between LP plastic limit, the liquid limit was about 70 to 80, and water content was very high, usually higher than the liquid limit. It's a very soft clay. So this is the unit weight, void ratio, and here drainage strength carried by the VST, which is the vein shear. We're going to talk about that later. And these are remolded, and this is these are remolded data, and these undisturbed samples. Okay, and we're going to talk about this later. And at the time, I plotted all the results, but everything this was carried out from 1973 to 1978, so a very long time ago. And in those days, we have to plot it manually. So uh, with a lot of difficulty, I had too many data points, and this was tough. I spent months in the laboratory doing these uh, unconsolidated, untrained UU tracks or tests, and at that time, I came up with these average uh, correlations, and I found out this was the best. I mean, I was using 125 millimeter diameter sample, and the specimen was 35. So I changed the specimen diameter as well. Okay, and recently I did additional analysis by using artificial intelligence. I submitted the plots I have I didn't have the numbers anymore. They were lost. But I submit the plots I had, uh, manual plots, to AI, and AI did a lot of things. I learned, it took me 1 day to do this kind of analysis that in the past would take 2 weeks to do this. And these are the results. As you see here, this is the 50 millimeter sample, 50 millimeter specimen. The average result of the undrained strength is very low, definitely due to uh, remolding, sample remolding. And then as I increase the diameter, decrease the specimen diameter, the strength goes up. As we see here, this 63 is very good. The average here is more or less the same as this one. Okay, and this is 125 by 100. Uh, I took the specimens were 100 millimeter in diameter, and the results were not very good. And this is the best that we had. Okay, so I by taking a large diameter sampler and a small diameter specimen was the best that we got. Okay, and then I did some comparison with the field vein vein shear test, which we're going to address later on, and because this is an in-situ test. So, which uh, how to correlate this vein with U tests? And what I found is that these with D over D capital over D lowercase 3.24, the average is about the same, and this allowed me to calibrate the field vein test. I mean, to correct, not to calibrate, to correct. As we are going to discuss later on, vein shear tests in most cases have to be corrected by a factor of less than one. And in this case, in this project, I found that with the artificial intelligence, we did all the plots for me, the best correlation would be with the correction factor of 0.7, which is typical for. Well, let's dive a little bit into hard rock sampling. And there are mainly two ways of doing that. One of them is by using a rod, okay? But if you are going very deep, you certainly need uh, a wireline procedure or device in which the sampler is lowered into the the borehole by means of a wire line, and then you pull it out. You can you start the rotation, and then you pull the this the sample out. There are different types of samplers in different diameters, and some of them they are triple barrel. I mean, why double, triple? Because if you rotate with the sample inside, if you rotate the sample, you're certainly going to disturb the sample, the rock sample. In this case, we can use a double barrel or a triple barrel, which is much better. As we improve the sample, the amount of the the size of the rock sample is increases. So in a case like this, you certainly do a very poor a very poor sampler and procedure, which leads to lots of breaks on the sample. Okay, these are simple, which simple has one barrel only. This the drill bit, this the valve. So this is not very good, leads to bad results, and you should use at least double, sometimes triple, and you can have the retaining springs down here in order to avoid the rock sample to fall out. And these should be the best one, stationary line samplers, in which you have a liner inside to make sure that you have very good rock sample. So you may have springs or no springs, it varies, okay? And this is the Denson sampler for hard soils. So if you get into a soil of SPT over 20, you may use this to get a good sample. And this use the Q5 sample quality, as I've told you before. And some of them, this is a sample without spring. It has the spring here at the bottom, but not at the top. And there are some advantage, adv advanced models with the spring here, which controls uh, the force here at the beat. So it's a better one. And also what we do uh, when you get the samples, rock samples, you put them in a box like this. Usually these boxes are plastic ones. In the past, they were all wooden blocks. Now, wooden boxes. Now it's plastic, and you mark the depth, etc., sample number, etc. And then the next step is the geologist analyze. He described the lithology and also the RKD, which is the sum of all pieces longer than 10 centimeters against the total length of the sample. Okay, so this is a simple way of calculating. This is a very important parameter. The other thing that it's very much used today is a borehole endoscope. And like the endoscope that I use in medical procedures, we had a camera. The camera enters the borehole, and it's going to show you what's going on. You can measure. You can have a much better description of the lithology. You can have a description of the faults, joints, and you can carry out a stereographic uh, plot of the joints. This is fantastic, a fantastic equipment. It doesn't cost too much, you know. It's very good. Uh, I'm going to address a little bit of geophysics. I don't know very much about geophysics. I'm not a geophysicist. I only advise in some cases when we should have a geophysics. I'm going to address this very briefly. And there are two geophysical methods which I love. In most of my projects, I have this. One of them is the MASW, which is the multi-channel analysis of surface waves. Uh, then this is relatively cheap because you don't have to carry out any borehole. You do everything from the surface. All you have to do to stretch these geophones along, a certain pattern, predetermined pattern, and then you strike a plate, you give a blow, and you acquire the signals. And what are the? I don't know how to calculate that. It's not my area. But what we get, this is very important. We get a VS profile, which is the shear wave velocity profile. Or we can have also VP, but VP is not that important for geotechnical engineering. Can be used, but not that important. The most important one is the VS. And why? Because VS is directly related to, according to this equation, if VS is directly related to the shear modulus of the soil, of the material. And this shear modulus today is a must in most cases that we do numerical analysis, we do numerical modeling. This is very important. The other thing that's very important to have in many situations is to carry out electroresistivity. These can locate the rock, locate the water table, And I always have a geophysicist helping me to analyze these data because I'm not a geophysicist, as I've told you. And this is a case of a slope in residual soils in which we want to put we want to discover where the water was. We want to store subhorizontal drains deep into the soil to extract water. And here at the blue areas is where we have uh, we have the water. Okay, we have much more water here, and these areas which are yellow or perhaps red have much less water. So by doing that, we were able to install these subhorizontal drains exactly where there was a lot of water. Okay, so this is an example. I use this for many situations to locate the water table, locate the rock bottom, things like that. I have used also electroresistivity for tailings dams to locate water where water was. And this has excellent results, provided you have some boreholes also to analyze. And in the end, what you want to get is this a geotechnical profile in which you have a fill. This is clay, this is sand, and this is very hard clay. An example, and here the SPT values, as you see, in the field they are very low. They are mediums from 7 to 10 here uh, in this clay. In the sand, it varies from 15 to 30, nearly 30. So this is what, as a geotechnical engineer, you want. Regarding in situ tests, we have two kinds of tests, profiling and calibration. What's a profiling test? A profiling test uses the stratigraphy, but parameters are extracted from correlation. And we just have seen one, the SPT is a profiling test. But we have also calibration tests in which stresses and strains are known and parameters could be obtained by numerical modeling. These I'm going to these are kind of profiling tests, SPT, CPTU, market dilatometer, and Vinci test. We are going to cover CPTU and VST, but not the market dilatometer to the lack of time. And calibration tests, the most important one is back analysis of structures. Also, in addition to that, we have self-boring pressure meter tests, very difficult to carry out. I've worked 1 year on this long ago at UBC. The Menar pressure meter, that's something that's easy to carry out. Plate loading tests can be easily done, but it has a drawback, which the amount of soil in which it tests is only twice the diameter at a depth of twice the diameter of the plate. And can be, in the past I have done also horizontal plate loading tests, but I don't use this very much today. I prefer to use, when you have a hard soil, Menar pressure meter. Self-boring is very difficult, very expensive. I decided not to use that anymore, although I have used it in the past. And a typical property variability. This is something that we have to understand. So if you are looking at steel, concrete, and timber, these variability is very small. Why? The coefficient of variation is small. Why? Because these are steel is a man-made product, so it can be very well controlled. The properties are well controlled in a factory. Concrete varies more because it's cast in most cases it's cast in place, and you don't have all the controls that a factory has. But timber, which is a natural material, it's much higher. It's nearly 25% of strength. And let's have a look at the in-situ test repeatability. This was, I attended long ago, a seminar about the late Professor Kulhawi, Fred Kulhawi. and I learned from him this. The SPT varies a lot. Why? Not very much control, so it has a, but it is very important. Although we don't have a lot of control, but it's very important because it yields at a lower price, usually reasonably lower price, some important parameters. This mechanical CPT, which is no longer used, I used that in the 70s. CPT very much, and as you see here, the variability of the results with CPT is very small. Why? Because you don't have the effect of the operator. Everything is automated. The VST also has a larger variability. Why? Effect of operator and other causes, which I'm going to address later. The dilatometer also, as the CPT, presents a very small variability. Pressure emitter is much more. Why? Because the pressure emitter, you have to drill the borehole, and anytime that you drill, you remove the soil around, etc., etc. But it's a good test for hard soils. And self-boring pressure emitter is something which I'm not going to address because it's too difficult to carry out, too difficult. In relation to soil properties, in most cases we are interested in strength parameters, and strength parameters, it varies, especially the undrained strength varies a lot. This is a coefficient of compression coefficient of the Virgin curve in a odometer test. This varies a lot, and also void ratio. This reasonable, okay, but as you see, the least variability is of gamma, the unit weight of soil, and that's the reason that we can relatively easily estimate this from a few tests. Doesn't vary too much. Okay, SPT correlations. There are many. I'm not going to address them all, but this is for me is the most important one. When you get the E50, what's the E50? The E50 is Young's modulus related to 50% of the stress level, of the maximum stress level. Okay, and this is a kind of correlation that I use a lot. The E50 is about 3 to 4 SPT. Okay, and if you want to know more about correlation, I would uh, recommend this program, which I have used for a long time. Is a program which was written and provided by this company. Is a Greek company, Geologmis. I have been working with these guys from a long for many years now, nearly 15 years, and we developed some programs together. And here you can have all these correlations, settlements, VS, joint strength, friction angle, relative density of sand, the N6 to N160, which is corrected. So you just come to use the software, you open it, you slide this right and left until you have the SPT value that you want, and then lots of correlation. The problem is varies too much. For instance, for ES, which is Young's modulus, it can vary from 10,000. Here's the least one, Gravely Sand, 6,000, 66,000. Oh no, this is the, the least one, 33,000, because it's a silty sand, and goes up to 30,000 for normally consolidated sand. So, but over consolidated sand is 45. So there's a big difference. So that's why you can't rely only on SPT. SPT gives you a direction, but then you have to do additional tests in order to get parameters. Okay, these recently Harry Poulos published this recently in a he gave a webinar that I attended. So this is a kind of correlation SPT with VS. The VS is shear wave velocity, the good correlation. Also, ultimate capacity for shallow foundations. The capacity for shallow foundations is K times N, and these the values of K. So, now I have to ask you, what is a property? A property, this is a definition I heard many years ago, 20 or more, 30 years ago, from Fred Kuhari, the seminar I attended, given by him. A property is a value that you use a numerical model, a specific numerical model, and then it gives you expected results. So what I learned from him many years ago is that there's no value of a property without the numerical model. You have to combine the two. And here's some hints which I learned. I started doing numerical analysis, I think it was 1999, and I used FLAC in the beginning. Later on, I passed it to Plaxis, and I used Plaxis from 2000, and we still use it. So 25-year experience, more or less. And when I started using Plaxis, the numerical, the constitutive models they had was mainly more Coulomb. Plax was in the early years. So by using the Morcoulon constitutive model, it assigns a loading relationship, which is the Young's modulus. And if you assign this, but if you unload the modulus is the same. So there's no difference. E loading is same as E unloading or reloading. Okay. So this for excavation, which I designed so many excavation in my life, it was a big problem because I learned later on, but in the beginning that was available. And what was wrong? Displacements at the bottom. I show you some data. And why we need better tests? One of the reasons is to get this curve, which is not very far from a hyperbolic model, okay? And later on, Plax came not only with a hyperbolic model, but with a hardening soil model. And this was a major advantage in Plax. It changed everything. Up to date, I use this a lot. What's the difference? The difference that while the Morcoulon method or constitutive model is like this hardening soil model, they use a hardening hyperbolic model, which was the hyperbolic model was developed long ago by James Duncan in America. And in addition to that, it has we can use up to three different values of modules. The most common one is the E50, which is this at a stress level of 50%. But there was an advancement of this model in which it was developed to use the small strains which take place in the beginning. This makes a big difference. But in addition to that, the EUR, which is the unloading reloading, is much higher than the E value, the E50. And this is very much close, is the best way of, one of the best models to analyze excavation tunnels in which we have excavation and sometimes loading as well. So this is the constitutive model, and this is the hardened soil model. And later on, they developed this hardened soil small strain model in which they added the E naught, which is the Young's model for very, very low strains. So This is what I like to use, and this is why we need small strains measurements, which can be done by geophysical methods. This is what I found, exactly what I found. If I used a standard Molecular method for the excavation, these analysis is going to show very high displacements at the bottom. Why? Because we are not using the proper module for unloading. While if you use HSM or better HS small method, we get much better results in terms of moments, but better yet in terms of excavations. Okay, and this is kind of an application for tunnels. It makes a big difference. The hardened soil is a much better constitutive model. Sorry. This is how actual soils behave. They present a lot of nonlinearity, and this is the small strain models. This is the shear models relative to some uh, some stress level. Okay, and this is something that came up long ago. I first saw this in the 80s, in the mid 80s, in which this is a degradation curve. This strain, shear strain, and this is the relationship between G, shear models at some strain, and the G naught, which the high one, and the very small strain. And this we can separate into three areas, in which in this area for in between 10 to minus 5 to 10 to minus 3 uh, gamma or shear deformation. We have micro deformation domain. Here's the mid, and then here we have the macro deformation domain. But in most cases, what we have in terms of triaxial tests most triaxial tests are in this area. Okay, this depends on the type of test that we carry out, and this kind of how to relate very small strain, larger strains to uh, retaining walls, to foundation, to tunnels, and most conventional soil testing. So what we do know is that if we degrade the modules by, say, multiply by 0.3, we get data very close to E50 or something like that. Okay, so how to extract parameters? Boreholes and SPT, geophysics, mainly VS. VS is much more important. In-situ tests, soft soils. These are in-situ tests on soft soils. Hard soil, I use PMT. And of course, laboratory tests as well. And the final discussion in this presentation is how much investment on site investigation. The amount of investment on site investigation varies according to the risk of the structure. So this total increase in construction costs and related to the amount that we invest on site investigation. What is shown here? If you in many cases, if you invest very little, you may have increasing cost of the solution, the technical solution, of say 50%, 6%, something like that. And if you invest more, you get almost no or very much less increase in construction costs. And this is an idea depending on project type, uh, buildings, highways, dams, and tunnels. Dams and tunnels, they are very risky structures, and so that's why there are recommendations for investing something like 1 to 3 to dams and over 3 to tunnels. which are uh, very risky structures. And this percent of the foundation costs, which could be 0.5 to 2%, 1 to 5, 1 to 5. In my experience, I, I always take into account how much we invest on highways, dams, and tunnels, especially tunnels, that we should invest more than 3%. And the International Tunnel Association has this manual, which I recommend you to download and have a look. They show you what kind of how much you should invest and what kind of investment should that be. And this is a very interesting recommendation. Then we finish this part. I'm going to make a 1 minute break, maximum two. 1 minute break, that's enough. And then we go to the last part of the last section. Okay? So let me stop here. Okay. One more. Okay. Okay. Well, let's talk now about CPT and with a brief comments on uh, a brief comment on VSC as well. So are the main tests that we have just presented SPT and boreholes as well, sampling. We we're going to talk now about CPT and a little bit of VST in the end. Okay, so these are the main reference, the same as I've shown before. And this is the history of the CPT. The CPT started in 1931 by a guy in Holland. And I wonder why, if you can, there's a question for you. Why they decided to develop the CPT in Holland? And why didn't they use SPT. Question for you. You let me know later on. You can email me the answer. Okay. In 1946, just after the war, the Houtse Machining Fabriek in Houtse, also in Holland, developed a mechanical cone. 1947, the mantle cone that we use. 1964, Fugger developed the electric cone, and Bigman in 1969 developed the friction cone. That's the first cone I have seen in my life. Later on, the Torstensson from Sweden developed the piece of cone, and UBC developed the seismic cone, which I also used and analyzed some results that I'm going to show you. UBC at the University of British Columbia. So the original cone was trying to simulate a pilot installation. So it has they want to separate the tip resistance from the friction, and that's what the Dutch started. They use a rod which is 35.6 millimeters, standardized everywhere. And in the beginning, they later on they came with this mantle in order to measure the local friction. Okay, this was the first one, and sorry, the local friction is measured by this one, which was the Begeman cone, in which they could push the tip, push the mantle, and push the rod. So this was the first. I've seen it in 1971. Yes, it was developed in Holland in 1969, and Frankie Pyle was using that in 1971. And I visited there. I was a student, engineering student. I visited the site to see how they carried out the CPT. And Fugger developed this in 1964, 1964, yes. And so it was totally electric, but not as good as the electronic that we have access today. And it has many advantages. One of them is quick, accuracy and repeatability, very accurate, continuous profiling. We usually take measurement at each 2 to 5 centimeters, okay, along that. Today, we can have digital data. And when I started, we just had analog data. It was terrible in the early 80s. Then we can do a lot of data processing. Today we have programs which I'm going to address about that. Parameter extraction through correlations. But what's the advances? Since the scatter of the results, the accuracy, is much higher. So the parameters obtained by a CPT is at least one order of magnitude better than those obtained by SPT. Those advantages cannot be pushed through through hard layers. For instance, if you have gravel, it's not going to be pushed there. And also in hard layers with SPT over 30 doesn't we cannot push. It's impossible. Many standards around the world. The STM standard here is very good. One for the electric cone, the STM D57778. But there are other standards. Wherever you go, there's some difference. But the American standard is a good one. I can assure you. There are two types of cones. One is a subtraction cone, in which we have the one cell measure the tip resistance, and the other one measure the total resistance. And then you have a subtraction type of load cell, and you have to do this. And on the other hand, we have a dual cell cone with separate cells for the tip is totally separate for the sleeve friction, which is here. This is more robust because this piece here is very robust. But this, on the other hand, is more accurate friction, sleeve friction data. Okay. And this is an attempt we have done in my university in 1975. It was just before I joined the university as a professor, uh, 3 years before. And this was a thesis carried out by uh, someone I know, Camilo Borges, in 1975, and he developed, with the help of a mechanical workshop, etc., electronics as well. He developed a cone, which, well, of course, was you know uh, technology of the time, and we didn't have the digitalization of data. The data were all analog using this. Later on, I worked in Fug in the 80s. In Europe, I worked in Britain in that time. They still use this kind of digital analog device. Uh, anyway, uh, later on in 1994, we set up an electronics laboratory with uh, electronics engineer, and we decided to develop our own cones. So this is the guy that worked with us. We also, and then we designed and built some piezo cone with 50 or 100 MPa capacity to measure side friction, pore pressure, and tip resistance. And this calibration frame that we designed and built, we used that for all the cones that we have used. We developed in 1994 also a data acquisition system. This guy was a electronic engineer, and he wrote the program for us. And this is how it showed. We had measure of tilt, QC, which is the tip resistance, uh, side friction, and pore pressure U2. This was how the operator would see that. And we used in the first rig that we used was very tough, very similar, very rough, and sorry, very rough. And this was manual operated. We used this rig for the mechanical cone and the early electric cone that we used. This is when I spent some time as a visiting professor at the UBC, University of British Columbia in 1990-91. I was part of the team, and we used this truck. It was very advanced for the time, and uh, much faster to do the work. We used to go to the field once a week, and then we spent the whole week to analyze the data. It was uh, heavens on earth. And this is, I worked in Hong Kong as well in 1996 and 97. And this was the truck that Fugro had. And I worked with this company as well a little bit. At this time, the digitalization was available. Okay. And this is the first seismic test that we carried out in Rio. Uh, in 1995, we used this kind of mobile rig, but of course, it was not the technology we have today, but it was an attempt, it was a research project. Also, we did lots of work, lots of tests in other projects in South America, like this one in Ecuador, Baba. We adapted the existing rigs to do that. Uh, so we just sent a technician with the cone, and we adapt the existing equipment on site to do this kind of work. And also this is somewhere was for a dam as well, and this was in Peru, very cold, Antamina mine in Peru. We did tailings, and this is the truck that we used from 1994 to 2005. And this is a visit when I went to take a course of Praxis, a Praxis course in Holland in 2001. I visited this site, and this was by far the best CPT truck I've ever seen up to now. And it has what the name crawlers, and everything is automated, one operator only. Uh, Marvelous equipment. It has uh, two two piston two piston system. So there's no they don't stop pushing. It's continuous. Very interesting. And this is something that we had to do in Amazonas River using a adapted barge and a drill rig like that. So uh, it worked. Okay, this Amazonas River. And sometime in, I think, 20, 20, 2010, we bought this hydraulic rig, which is is small, very easy to take to the field because the truck, in many cases, you cannot go reach the location where we want to do that. And this machine is really fantastic. We still use it. And this machine using on tailings, and here how to prepare the CPT. This is people carrying out the tests. We had this tent in which the computer was here, and this is something that was developed by uh, Sacchetto. He's a friend of mine from Italy, and he developed the CPT while drilling. Why? I show you. This is a case where CPT while drilling is needed. Is when you have iron tails, there are many very stiff layers in the tails, okay, that the normal CPT will not go down. So we have this kind of these CPTs carried out with normal equipment, and it doesn't reach the bottom of the tails. And to solve this, Massimo Sacchetto developed this kind of equipment. He's he has a very good mind to develop things like that. And so this is operated wireline so that you can drill up to where you want, and then you lower the, the, the cone, and the cone latches via the bottom of the drill bit, and you can push the cone. And this is how the equipment works. And he helped us to develop this, to make one of this. And this is the kind of CPT that Massimo Sacchetto has carried out down to 100 meters. So, which is not easy to with normal equipment. And this is the what we have done to to develop the CPT. We have the drill rigs adapted. We have this uh, drill bit adapted as well. Here's the cone, and this is the test we have done. This the I mean the computer screen that we follow up, and this is the kind of result that we've got. Uh, we drilled up to 15 meters, and then we found this play, mainly play here, and this the cone resistance, friction ratio, pump pressure, and this is how the data are analyzed in order to obtain the behavior, the soil behavior type. I will address this later on. Well, in the field, one of the very important things is to do the saturation. And we have this kind of machine. This is a sonic bath, which is available in most workshops. And this is something that I found out when I went to the dentist. They had a suction pump, a vacuum pump, a small one, and I searched the market in those days for medical equipment and found this and bought it. And we do the saturation previously in this. The other thing that we I learned how to do. It was with late Professor Campanella, how to do the saturation of these elements in in the field. Okay, and we use a cone like this, a plastic cone, uh, and we use a syringe and insert the liquid. Liquid can be either silicone oil or a mix of uh, mix with water. Uh, and this is when Professor Campanella gave me a class on how to do the saturation. This this slide that I think that was 1990 or 1991 while I was at TBC. And this is the cone ready. We use condom to prevent the water to maintain the saturation. Uh, and this is the quality of pore pressure measurements. If you have poor saturation, that's what we get. Okay, you're going to see this part, the this the pore saturation is very bad, so we have this. But here the saturation improves. Why? Because the water pressure is high. And this is something similar, but we have very poor saturation here, and we see from the zigzag that here we have much better saturation. It was a much better response for depth in addition to 10 meters. And this is a very, very well saturated, very good saturation. We see from the results how well is the saturation because it presents the clear detection of thin layers and seams. Okay, uh, this kind of test I have done long ago. It was uh, uh, first of all we tried to push the blue line. We tried to push the cone from the start, from the ground level. Okay, and then I didn't like very much the results. I thought the saturation may not be very good here, and I decided to do something different. We carried out a small borehole, 50 centimeters, 1 meter, I don't remember, and we filled with water. And then we pushed the cone again, okay? And this is the result that we had, which shows clearly that the saturation in the blue line, the saturation loss, and he is much better. Okay, so we have the zigzags. Here is where we did dissipation test, which I'm going to address. Cavitation. Cavitation is when the cone is pushed through a very high strength material like dense sand. If you do that, you may generate uh, negative pore pressure. And this is what happened. The saturation was not bad, but when we reached this level, there was a loss of saturation due to cavitation. And this is something which is very difficult to avoid. But you have to look at the data and see if there was cavitation or not. Di Campanella, the late professor of the sea, devised this and published, I think, 1988, something like that. He found out that the cones uh, have a different unequal end areas like this. AN here and AT here at the tip. And this is very difficult to avoid this correction. All cones they have this kind of unequal end areas. Okay, uh, it was easy to avoid the unequal end areas at the friction sleeve just by machining the with the same diameter. Okay, but at the tip is impossible. And how to do this kind of how the Professor Campanella found this? He put the cone into water, applied pressure, water pressure, and obtained this this is the kind of relationship they have for one cone. And in most cones, what we have is the QC is it should be 45 degrees here. It's not. Okay. And this was Professor Campanella told me that if Fugro observed these results in offshore work, but they didn't have a solution. And Professor Campanella found the solution, and he came up with this equation to do the correction. The correct with tip resistance is QC plus U2, the pore pressure measured here, 1 minus A. And A in most cases is 0.8. In good cones, it's 0.8. Stratigraphy. Stratigraphy increased a lot. This was in the early days in which was easy to find where there was sand and was clay, sand high QC, and clay low QC. This is uncorrected tip resistance. Okay, and this evolved a lot. While I was at UBC, I wrote a program to do this kind of analysis, and this is one of the tests that we carried out in Richmond, British Columbia, in Canada, in 1991, in which we have the QT, RF, U2, and at that time we had one software by Professor Campanella, but it was not very good. Didn't make the plots, so I did all the plots, and this is another example in which we can detect sand layers. That's the same as this one, but here we are trying to analyze where there's sand. This is clay. This is sand seam. This is a clay seam. This is a sand seam. Very clear from here. Okay. And this was a soil classification that came up in the early application in the 90s. It was developed at UBC also, and the soil classification that we use today is the development of this, the improvement of this, and this was a classification based on pore pressure measurement, which is not used anymore, especially in land applications, onshore applications, in which I've shown you the too many errors in the measurements of pore pressure. This this was proposed by Professor Yambo and someone else, I forgot his name, but they wanted to do that. This can be used for offshore application where you have very, very high pressures, and the measurement is usually much better. But onshore application, not. This came up then at UBC by Peter Robertson, was initial soil behavioral type, in which we related QT to friction ratio. When you have a high friction ratio, in most cases you are in place. When you have a low friction ratio and high tip resistance, you are in sands. And something that was very important that he did was to normalize the colors. So it's very easy. If you look at a graph, you happen to use one of these softwares, just by looking at the graph, you know which material you are testing. Later on, Peter Robinson decided to normalize, use normalized parameter for tip, for friction, and for pore pressure. Okay, and we have this. This was a development that came after some time. This was published in 2009. This normalized behavior, and now there is an additional development that came up in 2009 too, which the SPT, any normalized behavior. I won't go into very much details of that because I want to show you how to do the processing and use of CPT data. This is the kind of program I have written while I was in UBC. So early processing techniques, we use the CPT inks written by Campanella and his team, and but it didn't plot. So I decided to plot the results to do the analysis, and this is what I, I did at the time. And this is a very interesting. Uh, these are very interesting data, which shows how the cone can detect sand lenses in clay. Before that, before the cone, it was really impossible to detect that. And these sand lenses, if you have a lot of lenses in which this material in Santos has, uh, I've done one of the tests there of an embankment on weak drains, and the weak drains did not work in the end. Why? Because of a lot of sand grains and sand lenses. In the beginning, it was impossible with SPT to detect this. These are the software developed. Now we have a wide range of software from many companies, and this is the software that I use when I work with D Campanella. And now I use this software, which was provided by this Greek company, and I work with that. And this Greek company had a strong support from Peter Robson as well. So all when I started working with them, the software was not very developed. I gave them many ideas and I checked the data, etc. I worked with these guys since 2009, and now the software is very good. And this CPT IT processing, this is the same plot that I have done before the uh, with the Sigma plot. And now it's much better because this software finds which kind of material you have. This, for instance, you have, in this case, is a fill, mainly silty, sandy fill, and here's clay. Okay, these are uh, very homogeneous software. And also, I've done a lot of work on gold mines, and not only gold mines, but iron mines as well, in tailings, mine tailings. And these are characteristics, a very interesting characteristics of many mine tailings. This case is a gold mine. I worked with these people for 7 years or so. And this is the cone resistance. And if you see these zigzags, this is typical from mine tailing. And why? Because there's always a cycle of drying and wetting the mine tailings due to the way they are deposited. So that's why we have this. Also, you have the zigzag in the pore pressure. Why? Because in this case, this gold mine from Quiros, they have a very high CV. Oh, I forgot to use this. Sorry about that. Uh, they have a very high CV. So when you changing the rods, the pore pressure reduce a lot. So very interesting. These are kind of iron ore, more or less the same stuff. We have these many zigzags, not as much as the gold mine tailings. And here we did a lot of uh, dissipation tests, which I'm going to address. And this kind of material that we have, it's a silty. These are silts. Uh, Interpretation in clays. This is one of the deepest boreholes, CPTU boreholes that we have carried out, CPTU tests, down to nearly 45 meters. And this is proportional. This shows very good results. Okay. And what we have here is mainly silty clay. Okay. Uh, how to get some parameters? I will give you some ideas, but not everything. because it takes too long. The endurance strength can be obtained by one of these equations. This is what we use a lot, which endurance strength is Qt minus the vertical stress, total stress, divided by this parameter. In most cases, the NKT is 14. In the software I use, CPT, we can change this if we need. But in most cases, I can assure you 14 is very good. And that's inbuilt. There are other ways of doing that. This is was proposed by Main, this equation here. We get first the OCR. OCR is 0.305 from this. And then we have the undrained strength ratio, which is a function of the OCR. Okay. And the other thing that we have to do a lot is whenever you're dealing with soft clays, you should have what we call an island of in situ testing, in which we take samples to do laboratory testing, and we do vein sheet testing very close, 1 meter, 2 meters away from the CPT, and compare the results.
Professor,
yes?
We cannot hear you.
Sorry?
Can you hear me?
Yes, yes, I hear you. Well,
Yeah, you check
Can
your
you-
speaker. Can you hear us?
let me see.
No, we cannot hear you.
Oh dear.
Would unplug your speaker. Probably loose.
Okay, okay. Sorry about that. Can you hear me? Hello? 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 Can you hear me?
Okay, people can hear him. That's fine.
Okay. Thank you. Sorry about that. Anyway, I was showing this slide from a particular site in where we carried out an island of site investigation in which we had this we had the laboratory tests to get tobacco limits, unit weight, void ratio, and here we have the CPT and the VST, and we see a very good correlation between the two. And this is not all, this doesn't take place always, but we always should, when we are dealing with soft clays, to do CPT and a VST very close. Okay. Deformation moduli, there are many equations like that by Yambu. That's Yambu's modulus, one-dimensional modulus, Young's modulus, and with different values of alpha, which give you the correlation. And this is a kind of correlation that was proposed by Sangleha many years ago in 1972 for different types of soils. But everything is built in the program. You don't have to, provide you use a good program, you don't have to care about this correlation because they have already that inbuilt. And these are kind of also Yambu's modulus, one-dimensional modulus, in relation to Qt minus the vertical stress over atmospheric pressure. This was proposed by Kuhari Main. And then once you have the Qt, you can estimate this program, CPT estimates the one-dimensional modulus. Here's the yield stress. I mean, they calculate the stress if you have a foundation of some breadth, and it calculates automatically settlement. What my experience with that is that this works perfectly. this, for me, is by far the best way of obtaining settlements, especially in soft clays. But I would recommend this very much. This is much better than carrying out, even with very good laboratory testing. There's a lot of scatter in the data, and this is precise. I happen to carry out some instrumentation on a project that we had settlement, and always the difference less between prediction and measurement is less than 20%. So this is by far one of the best methods to do. In the past, in the 90s, I used to use the dilatometer because dilatometer was very good for predicting settlements. I'm not going to talk about dilatometer because we don't have time. But uh, this the analysis, this kind of analysis improved along the time. And today I can say that this is by far the easiest and the best way. This is very reliable. I recommend the use. Well, interpretation in sands, we can obtain relative density, frictional angle. This is a kind of relationship between N, SPT and which can be used, but you must have the diameter of the sand. And this was kind of correlation by Campanella and Robson in 1983, and this was relative density by Yamiokowski 1985. So we have this is another correlation for E50, uh, Young's modulus, and I show you uh, some results. This is the one of the deepest, as I've shown you before, one of the deepest uh, deepest CPT I've carried out down to 45 meters. And now I'm going to address very briefly the Vinci test and what the problem we have in America. This Vinci test, which was devised in 1919 by the Swedish uh, by the Swedish, and in most cases, if you have the height of the vein equals to 2 times the diameter, you can calculate the endurance strength by this formula, in which T is the torque in kilonewton meters, and this is the diameter of the vein, and you do 2 tests. One undisturbed, and then this depends on the standard, but in most cases you just give to the vein 10 full rotations. You rotate the vein 10 times, and then you do another test, and you get the remodeled value of endurance strength. I did a lot of work on this, and I won't be able to talk about this uh, because we don't have the time. But this is unprotected vein borehole. I thought in the beginning that it could work, and we did a lot of work on that. Then we have the unprotected vein, protected rods. This was French design from the 80s. And then we have today the torque cell, which is, if we use this, is okay. But in 1990 something, no, yeah, yeah, no, 1980 something, we designed. I worked at the Road Research Laboratory, and we have a mechanical workshop. So one of the mechanical engineers, designed something for me based. It was not a original design, but it was based in a Swedish previous design, previous idea. We had the protection shoe in which the vein was in. Then when you reach the some depth, we just we gave a kick here on the rod, and these advances half a meter, we rotate, and then we pull it back. This was an advancement in relation to this. And why? Why? This is what's very important. The American standard allows you to do a dummy test in order to get the friction at this rod. This is allowed by American standard STM. I published the result of this in an STM conference on shear strength, which took place in Tampa. If I'm not wrong, it was 19, no, 1988, something like that. And I showed that this kind of correction is impossible. We did a lot of tests to see if it was possible to do the correction. The scatter is so much, the scatter is so high that we found it impossible to use this kind of solution for the vein. We should avoid, it's a must, to avoid the friction. This is a way to avoid the friction. This is a way to avoid the friction as well. That's the only way it should be allowed. And the other thing we discussed a lot at that conference was that the American standard still allows the use of different shape of vein. And this was discussed very much at that conference, in which the idea is that this test is semi-empirical. It's not a rigorous test. It's not a totally empirical test. It's semi-empirical. And by doing that, you allowing different equipments, and this should be prevented. To the point that the Europeans went in this direction, and I wrote many years ago a standard for that, and we decided not to allow this. And it says this section of the standards, rod friction measures under no load condition can be performed. No, this is absolutely wrong. If you do that, the error could be 20, 30%. I'm sure of that because I did a lot of tests. And so these parameters can be estimated through that program that I've shown you, and we can compare the with VST data, undisturbed VST data, and these are remoted data. So we can compare the prediction from CPT with actual VST values and check whether or not a correction must be made. The other thing which is very important is dilative versus contractile behavior. And this is very important, especially to analyze the possibility of liquefaction potential. And in tailings, this is of utmost importance. And this is something that Peter Robs also developed, the KTUN value, the normalized tip resistant KTUN with this kind of equation. I'm not going to discuss this a lot, but he came up at some stage with this plot in which he is normalized friction, he is normalized tip resistant, KTN. And he found out that everything that plots below is KTN of 70, which is a curve like this, is contractive. And above that is dilative. And what causes liquefaction and volume change is especially contractive behavior. And then he came up with this plot. It's evolved a little bit. And 2016, he published this. Contractive behavior is is below that line, and dilative behavior is above that line. And I worked on Fundão analysis of the failure that took place and killed 19 people. That was in 2019, and this is one of the CPTs that I have had access. This CPT shows very clearly that here we have a very contractive behavior, and this is what leads to liquefaction. The other type of test, which is very important, is dissipation test. What's dissipation test? You stop penetration, you look at change in pore pressure at the porous elements in U2. And here you have uh, decrease in pore pressure, you have decrease in pore pressure, decrease in pore pressure, and here you have increase in pore pressure. And here you have no change at all, no dissipation. Uh, this no dissipation is because it's the permeability is very high. And so, what's the difference between dilation and contraction? This is what yields the kind of curve that we may have. So, if you have a sample that dilates during a triaxial test, what happens during the test? So, we have the particles going apart. And what happens to the pore pressure? The volume increases and the pore pressure decreases. So this is the behavior. The pore pressure behavior is linked to either dilation or contraction. If we have contraction, just the opposite. We have decreasing volume, and here we have the particles which are going to compress. And what happens if the volume reduces? The pore pressure increases. And this is what causes liquefaction in situ sand. Uh, CPTU designs. This was the first CPTU design by Torstensson in Sweden long ago. And then there were lots of designs. And this, I remember I was in Britain in 1980, 83 or 84, I attended a conference at the Civils, the ICE, the Institute of Civil Engineers, and they were discussing whether it was worthy to have the pore pressure measurement or not to have, etc., etc., etc. And now it's standard. Every cone must have a pore pressure element. And Di Campanella classified the position because there was different position. Fugro used to this U1 position. Today, most standard, including the American Society SM standard, requires position U2. You may have other position, but U2 is compulsory. You must have. And these are radial consolidation solution because when the pore pressure decrease, you have radial consolidation. Here are many solutions, and this one, hose is what most people use, and I use this as well because it allows the piezo-cone cavity, the nonlinear model, and any value of G over Cu, which is the stiffness index, rigidity index. And here's how we tend to plot the results. This is something that I work with that program, CPT. I advised them to do that. It's my contribution to that program. And testing as well. This is a typical dissipation test. And here we draw this line first. And then from this line, you obtain by half and half, obtaining this and come back to 50%, we get the t value corresponding, the square t value corresponding to 50%. And then we use this analysis of dissipation test by Boreholes VT, in which we come here with the t value measured. T50 is due to the U2 position, is from the numerical solution. R is the radius of the cone, and this is the G over Cu that the program calculates automatically. And then you have a number like that. The problem is this dissipation is in the horizontal direction, okay? And what we need in most cases is in the vertical direction, and also the stress level in terms of numerical consolidation, numerical consolidated. And this is an idea of what to do was proposed by Belli and Levadu in 1986, in which they how to do this kind of correction, and they proposed this number up to 6. My experience is that by comparing laboratory CV or field CV, in many cases, a few try and bankers that I've designed and built, and the correction should be something like 4 to 6. The scatter is very high. The other thing I'd like to address very briefly is the seismic cone. And why? I show you. Uh, what we are interested is the S wave. And why? Because we've told you before that there's a direct correlation, well, not correlation, there's an equation that we come with the S wave Vs, shear wave velocity, and transform into G naught. This is very important. So this is a kind of how the cone, one of the cone is made. I started learning about this while I was in UBC with the Campanella. And what they have to do is to install a geophone very in the cone. And then how we do the test, that's what we have done many times at UBC. We strike the plate with a hammer. We generate a signal, we generate vibrations. These vibrations reach the cone. And how we used to do that? We we used a 10 kilo hammer to do that, and we did we had an oscilloscope. The oscilloscope obtained this kind of signal, and here's when the S waves reached the cone, and we advanced the cone 1 meter. We repeated the test, and this is the delta t, the difference in time, in which we can calculate the velocity from in this region here, the midpoint. Okay, so velocity is delta L, which is 1 meter, over delta T, which obtained from the plots. The advantages are low cost. We can obtain a G max or G naught profile, marginal cost in addition to CPT. So we did a lot of that. And there's some very important application. As I've told you before, the wave propagation can be related to G naught in a rigorous equation, not affected by water. Okay, this is very important. And then in the 90s, I developed this program with some electronic guys that knew about signal analysis, electronic signal analysis, and this was passed to Geologs Week also, and they wrote the program for me, which is PAS, Signal Processing Analysis Software, and this is the kind of signals that we had. As I'm showing you, we strike on both sides of the cone, I mean right and left, and this is a kind of signal, and then we have to analyze and obtain the delta t from here. And to do this manually is very difficult, and we decided to use these guys from this signal analysis. They know very much about that. We decided to use cross correlation. It was a suggestion that was I learned from UBC, and these guys improved this cross correlation analysis. What's cross correlation? You have two signals. You have to determine the difference in time in between two signals, and there's a mathematical procedure that does it and calculate from the maximum, this maximum here, what shall be the done automatically when you compare two signals. So, and this kind of results we get from sparse. We have here shear wave velocity from left and right. Okay, they are close, so it's good idea. We have the unit weight from a correlation. And here, by having the unit weight, gravity, we can calculate G naught or G max. And this is one of the most important applications of seismic cone. When you're dealing with tropical soils in which they show a layer of lateralization. What's lateralization? When you have when you have dry, very long dry periods, followed by very wet periods, what happens is that the water that flows ingress into the soil, it dilutes the some minerals like uh, silica oxide and others, and these uh, it leaves some voids at the top, for instance, in this case, and this material at the top has a much higher rigidity. So why I'm saying that? Because I've done a lot of tests on this, and this is the shear wave velocity predicted by the cone, and it doesn't predict these increase actually measured. Why? Because these are laterites and the cone doesn't have this into their correlation. And later, after I've done all these tests, which I can show you later, uh, Peter Romsel came with this idea. He plotted QTN against G naught over QN, which is uh, shear modulus over the tip resistance. And what he found is that if you have a good soil, not with a microstructure, it plots in the red here in this area. But soil microstructure, cementation, bonding, and aging, in which the lateralization leads to, plots above this line. And coming to the end, we have a lot of experience and we have carried out many tests in many different types of soils, and we have a very good database to analyze. So we have in Canada, in America, here South Carolina, and all South America. Here we have in the Caribbean as well. It's missing here. We have done something like 90 campaigns in 7 countries, and these are tailings and these are soft clays. These are the main tailings and soft clays are the main type of soils which need CPT. And we came up. This is for soft soils in many projects that we have carried out. So we have this range of values that we can compare every time we do a new test. We compare with this, and we have also a database for undrained strength from many projects that we have. This is only part. Uh, Also, we have a very important database for CH. And why CH is so important? Because the scatter is too much. If you find something wrong, if you find something strange, you have to compare with other tests. And we have a database from many deposits of soft clays. So that's it, just in time. And I make myself available for discussions, for answering questions. Either you can do it now at the chat, or you can phone me or even email me. Before I finish, I'd like to show you uh, the program, how it works. Let me see. Uh, I have to. Can you see my screen or not? Hello? Can you see my screen here with the program? Oh, no, I think I have to share again. Let's share it again. Just a second. How do I see? Share. Okay, sorry. Okay, I hope you are able to see my screen. If anyone could confirm that you can see my screen, I would thank you. Anyway, here we have this is a very big project that it's ongoing now in Guyana. Guyana is the north of South America, and they have lots of soft soils. And what we can see from here, there are mainly two formations. This is the Demerara Formation, which is very soft clay, and then we enter into the Coropina Formation, or Coropina, in which we have medium to stiff clays and sometimes sands as well. And this is the pore pressure. As you see here, there was an improvement here. The pore pressure in the beginning was not very good, and we have much better pore pressure here. And this shows the Demerara formation in soft clay. Then we enter into silts. Okay. Uh, These the normalized plots usually I don't use. I only use this. And here we can see estimated parameters. So we have permeability, SPT, N60, Young's modulus, relative density, friction ratio, and here shear strength, either remolded or undisturbed. Uh, we can compare with uh, vein shear testing. And this is the case at the CPT7. We have a lot of vein shear testing here that we correlate very well with this. The other thing, let me go back, let go down. Ah, also we have uh, vein testing, but what I want to show you is this. Okay. Uh, no. Okay. This is shear strength. We can compare these are VST parameters uh, here, VST, and this is CPT, so we can compare. We see here the VST is a little higher, so it requires correction. These are uncorrected uh, undrenched strength from VST. In most cases, I use a 0.7 correction factor. And what's interesting here, these are shear modulus prediction. The black line is the prediction from correlations, and here you have the actual measurements of VS. Okay, very good. This correlations, the correlation is very good. And here as well, you see some points when you enter. This is the Demerara formation with the Coropina or Coropina formation. Also, we can, this is the shear wave velocity. As we see here, the shear wave velocity always slightly lower than the prediction in the Demerara formation. So this is the program, is a very interesting program which I use a lot, all the time. Okay, so if you have any questions, I'm available to answer. Or you can send me uh, emails or call me at any time. I'll be available. Okay, if someone wants to email me, I'll be very. Catherine wants to email. I'll be very happy to answer your any question that you may have. Okay. I'll leave. I'll leave here my mobile. Okay. I just wrote my contact details. Okay. Yeah, it's on the PowerPoint as well. Anyway, thank you very much. See you next. Bye.